Back everyone, this is where we left off, and as you can see, we were talking about the electrical conduction in the heart. So the pathway of electrical conduction in the heart starts from the SA node. We have a mnemonic, which is stab a big pickle. I have no idea who came up with this mnemonic, but it does sound odd, so it might actually help us with memorizing this. But I know by heart that this is the SA node, the sinoatrial node, and then we have the AV node, right, which is the atrioventricular node, and then you have the bundle of His, which is between the two ventricles, and at the end we have the Purkinje fibers, which go to around the ventricles. We can watch this Khan Academy video on it later as well. So the blood pathway starting from the right atrium was right atrium, and then the tricuspid valve, or tricuspid valve, because we're on the right side, and then right ventricle, and then the pulmonary valve, and then the pulmonary artery, and then the lungs, and from here it is oxygenated blood, so it is pulmonary vein, and then there's the left atrium, and then the mitral valve, or the bicuspid valve, because we're on the left side, and then the left ventricle, and then the aorta, and then we have the is it the like aortic valve, and then aorta, and then the and then after aorta there's the arteries. Then we have the capillaries. So arterioles, capillaries, venules, veins, vena cava, and then the right atrium. So we had right atrium, tricuspid valve, right ventricle, pulmonary valve, pulmonary artery, lungs, pulmonary veins, left atrium, bicuspid valve, the mitral valve, left ventricle, aortic valve, and then aorta, and then arteries, arterioles, capillaries, venules, veins, vena cava, and the right atrium. Cool. What is the heart's natural pacemaker? The natural pacemaker for heart is the SA node. So we should know that. So what is a natural pacemaker? What is a natural pacemaker? We believe that pacemakers are what give the pace to the heart, right? Like a battery. So is it? I hope you can see here. Is it like a battery? Cool. What is the part of the electrical conduction system of the heart that coordinates the bottom of the heart? It also electrically connects the atria and ventricles. It coordinates the bottom of the heart. So we because it says it connects the atria and ventricle, I believe it will be the atrioventricle node, which is true. But we didn't know that it coordinates the bottom of the heart. So how does the AV node coordinate the bottom of the heart? What transmits impulses from the AV node to the ventricles? So it should be the bundle of His that transmits impulses from the AV node to the ventricles. Again, we can ask, how does bundle of His transfer impulses from the atrium to ventricles? From the AV node to ventricles. What carries the contraction impulse from both the left and right bundle of His branches to the myocardium of the ventricles? So it should be the Purkinje fibers that transfers the impulse from the bundle of His to the myocardium of the ventricles. So it should be all like action potentials. Is it action potentials that transfer like a cascade from from bundle of His to Purkinje fibers? Myocardium. Myo comes from muscle and cardium comes from the heart. So myocardium of the heart is so myocardium is the muscle of the heart. And it says myocardium of the ventricles. We know that okay, now we're synced. Perfect. What are blood vessels that carry blood away from the heart? Those are arteries. Thick muscular tubes. Elasticity allows for recoil and helps propel blood forward. So these are the differences between arteries and veins and capillaries. So arteries are thicker, while you have a tunical media, which is thicker. You have a tunica externa, which is also thicker. It's elastin and collagen. The media is smooth muscle, and tunica interna, which is endothelial cells. But for veins, all three are mainly the outer two layers, the externa and media, are thinner. And however, the hollow section of the tube, the vessel, is bigger in diameter compared to arteries. And for capillaries, it's only endothelial cells that are covering the capillary. And instead of being in millimeter diameters, it is in micrometers. So it's a 1,000 times smaller. Now, why are arteries thicker yet smaller in diameter? Yet smaller hollow tube in diameter than veins. I hope that makes sense. There should be better ways to word this. We'll figure that out later. But we got the answer right. So, what are blood vessels that carry blood toward the heart? Those are veins. Thin walls with few elastic fibers. Pulsation is absent in veins. You don't have pulsation in veins. And that's why you don't need elasticity, right? Because it's not pulsing. What are tiny branches of arteries that lead to capillaries? So tiny branches of arteries that lead to capillaries are arterioles. We know this. We can skip this. What are one cell thick and make up the endothelial wall? So capillaries are one cell thick, and endothelial cells. But wait, capillaries are one cell thick and make up the endothelial wall. Is a diffusion of gases, oxygen, CO2, and waste, NH3, urea. What are very small blood vessels that bring blood from capillary beds to the veins? It should be venules. What is the part of the cardiac cycle during which some chambers of the heart muscle contract after refilling with blood? I believe it would be systole, because some chambers of the heart muscle, mainly the ventricles, contract after refilling with blood. So AV valves are closed during this. AV are atrioventricular valves, because you don't want the blood to go back to the atria. And the semilunar valves are open. Semilunar valves allow the blood to go out from the heart to other tissues. So blood pumps from the chambers into the arteries. You have the lopped up sound, heart sound. The first lobe is the systole. So you have the pressure in micro millimeters mercury. And as you can see, the AV valves close here. You have the aortic pressure, and it goes a bit down in the first place. When the so this is also the atrial pressure, and then suddenly the ventricular pressure goes up, where it gives you the boost in the aortic pressure. The semilunar valves close once, so the semilunar valves first open to pump the blood out of it, and then they close after the ventricular pressure comes back to 0, and the AV valves open in order for the blood to come in, which is the DUP sound. This small sound, I believe, is like a shh, where the blood is pouring into the atria. But we can figure that out later. It's not that important. So yeah, first the blood is filling into the ventricles. Then the ventricles, the ventricular pressure suddenly goes up and pumps the blood, while the AV valves are closed at the beginning of the pump, and when the pump is finished, the semilunar valves close. So the semilunar valves open at the same time as the AV valves close, and then when the semilunar valves close, it is the AV valves that open. So they have a reverse relationship together. What is the period of the cardiac cycle that encompasses ventricular relaxation? It would be diastole, as the ventricles are relaxing and the blood is pouring into the heart. So the chambers fill with blood. So during diastole, these semilunar valves are closed and the AV valves are open. Give the normal blood pressure range. It is 120/80 millimeters. So I believe the left one is for women. Does the normal blood pressure range differ between men and women? Blood pressure is sensed and maintained by what two factors? The heart rate times stroke volume. Oh, so it's sensed. Oh, what is sensing blood pressure? It's baroreceptors and chemoreceptors. So when you lose blood, you have both decreased arterial pressure, which is your baroreceptors, and you also have altered blood gases, which is sensed by your chemoreceptors. You have then the baroreceptor reflex and chemoreceptor reflex. And then there is cardiac stimulation, systemic vasoconstriction, flow and volume redistribution. There's also the Khan Academy video. So cons to watch. One is for the heart, the other is for baroreceptor and chemoreceptor reflex. The main function of what is to lower the blood pressure by promoting excretion of water and sodium. Oh, so what does excrete water and sodium? I want to say it's kidneys, but for lowering the blood pressure. So it is the atrial natriuretic peptide, ANP. So we need to figure out what this ANP is and what are we. And these are the major hormones in humans. Let's see if we find ANP, antidiuretic hormone. This is a good list. So ANP dilates the afferent arteriole, leading to increased blood flow and filtration, which results to diuresis. This is interesting since I said that it happens in the kidneys, and I believe this is the Bowman's capsule in our kidneys. So we have diuresis and natriuresis. ANP, atrial natriuretic peptide, lowers the blood pressure by promoting excretion of water and sodium. So what happens when you excrete water and sodium? When you no longer have water and sodium in your blood vessels, in your arteries, then your blood pressure goes down. It is because the water and the sodium increase the pressure of the vessel inside, right? When you have more water in your pipelines, the pressure is higher, right? This makes it also a good time to review the related concepts, which are the pressure laws, right? The pressure of gas and pressure of liquids. So this makes interdisciplinary relationships, fluids, and pressure dynamics. So we know that the ANP is a peptide, and it is a atrial natriuretic peptide. Now, Why does it say, oh, ANP dilates the afferent arteriole? So if it dilates this one, leading to increased blood flow and filtration, you bring in more blood flow to the Bowman's capsule, so you will be excreting more water and sodium. ANP can also suppress reabsorption of sodium in collecting duct and other segments of the nephron. It is a natriuresis. So, what is the difference between diuresis and natriuresis? How does di and nat change the meaning of uresis? So uresis, we assume that it is more urine. So you are paying more, you are excreting more water and sodium out of your excretion system, out of your urinary system. And as we see here, in two ways ANP affects the water and sodium. It's by both increasing excretion, so dilating the afferent arteriole, so there is more blood flow coming in, so it's diuresis. And then there is more reabsorption, so there is no reabsorption from the collecting duct, and it suppresses basically the reabsorption of sodium in collecting duct and other segments of the nephron. Aldosterone raises or lowers blood pressure, should be raising blood pressure, by sodium retention and potassium secretion at the distal collecting tubule. Interesting. So we have ADH and aldosterone both having the same purpose, to increase blood pressure, aka increase water reabsorption. But their mechanisms as well as action sites vary. So ADH, anti-diuretic hormone. So anti-diuretic means it is against your pissing. So it is, and we know that more urine results in lower blood pressure. So the ADH has a different mechanism than aldosterone. However, their purpose is the same. Their purpose is to increase blood pressure by increasing water reabsorption. So ADH reabsorbs water through opening pores. It works at the last part of nephron, the collecting duct. And aldosterone reabsorbs sodium and secretes potassium. It works at the second last part of the nephron, which is the distal collecting tube. So it can be misleading. And remember that liver produces angiotensin. So what is angiotensin? Is basically, I believe, the word for increased blood pressure. So although angiotensinogen, angiotensin 1, angiotensin 2, angiotensin converting enzyme, and then aldosterone, and then sodium retention, and then the blood pressure rises. So this is a perfect picture. We have the Bowman's capsule, collects whatever filters through glomerulus. This is the glomerulus. It contains urea plus anything small enough in blood filters through. And then we have the proximal collecting tubule. It reabsorbs all nutrients, reabsorbs most ions, secretes wastes, major reabsorption and secretion. And then the distal collecting tube, distal convoluted tubule, and these are also specific on what they reabsorb. So for example, in DCT, the aldosterone reabsorbs sodium and secretes potassium, and another hormone like PTH reabsorbs calcium. And PCT is a major reabsorption and secretion site. It reabsorbs all nutrients, reabsorbs most ions, secretes wastes. So we have the loop of Henle. It creates osmotic gradient. So the lower you go, you have a higher osmolarity, osmotic gradient. So there's more difference between the pressure of water and so it's denser here, we assume. Descending limb, it's water reabsorption that takes place here. And then we have the ascending limb, which is the NaCl reabsorption. Now, reabsorption means that it goes back to the body instead of being secreted as a waste. And we have a cortex of our kidney in the medulla. And here in the collecting duct, there is concentrate urine using osmotic gradient. And ADH can reabsorb water. There is a urea recycling and reabsorption and secretion of various ions. So PCT is proximal convoluted tubule, DCT is distal, pH homeostasis is tubules secreting H plus if blood is too acidic. They don't reabsorb, same effect as secrete. HCO3 minus if too basic. They have urea recycling. Urea diffuses out of collecting duct back into loop of Henle. It helps maintain osmotic gradient. So we need to watch with enzymes. And then urea recycling is urea diffusing out of the collecting duct back into a loop of Henle to help maintain osmotic gradient. The waste. So, what is urea recycling used for? Wastes secreted by PCT are NH4 plus, ammonia, creatinine, organic acids, and then loop of Henle. The longer the loop of Henle, the more concentrated the urine can be produced. We believe that the longer it goes down, the more concentration you have here, the more the denser it is down here. The countercurrent mechanism powered by NaCl pumps in upper ascending limb results in osmotic gradient down loop of Henle. Okay, we can come back to this, but this is a good representation from the MCATreview.org. Give the pathway of electrical conduction in the heart, so it's SA node to AV node to bundle of His and Purkinje fibers. What is the heart's natural pacemaker? It is the SA node. What is the part of the electrical conduction system of the heart that coordinates the bottom of the heart? The bottom of the heart is from the AV node. It connects the atria and ventricles. The bottom of the heart. What are one cell thick and make up the endothelial wall? It is the endothelial cells. Oh, it's the capillaries. They are one cell thick and make up. Oxygenated blood from what veins enters the left atrium of the heart? It is the pulmonary veins. What blood from the vena cava enters the right atrium of the heart? it is deoxygenated blood. The tricuspid valve is between what and what? It is between the right atrium and right ventricle. The mitral valve is between left atrium and left ventricle. Pulmonary what are oxygenated? It is the pulmonary veins that are oxygenated. The pulmonary arteries are deoxygenated. ADH lowers or raises blood pressure. So we know that ADH is the same as aldosterone, but they have different mechanisms, and but the same purpose they have is raising blood pressure by water retention through opening pores and collecting duct. So at the collecting duct, it opens pores and it results in water retention. So raising blood pressure. So we had this antidiuretic hormone, vasopressin. It increases blood pressure. ADH and aldosterone both have the same purpose, to increase blood pressure, but their mechanisms as well as action sites vary. So ADH reabsorbs water through opening pores. It works at the last part, which is the collecting duct. Aldosterone reabsorbs sodium and secretes potassium. It works at the distal DCT. Osmoreceptors detect increased osmotic pressure. Baroreceptors, aortic arch, carotid sinus detect decreased blood pressure. So if your blood pressure is decreased, it is via the aortic arch or the carotid sinus that baroreceptors sense it. But it is the osmoreceptors that detect increased osmotic pressure, aka blood pressure, right? So you have a hypothalamic neuron which releases ADH from the posterior pituitary, and then the blood vessels and kidneys are affected. ADH increases reabsorption of water at the kidneys, and it also results in vasoconstriction in blood vessels, so there is increased blood volume and increased blood pressure. If we look at here as well, we can see that ADH, aka vasopressin, is one of the two hormones that are secreted by hypothalamus, released by posterior pituitary. There is like 6 or 7 hormones that are released by anterior pituitary. So we should keep that in mind. And they're all peptide hormones. So the posterior pituitary is given the command by hypothalamus to release ADH, and it stimulates water reabsorption in kidneys by opening pores and collecting ducts. Right? Now, we should keep in mind that the other hormones produced by anterior pituitary are mainly with regards to it's different functions. 3 of them are female hormones: FSH, LH, and prolactin. And then there's the endorphins, which act in decreasing sensation of pain. They can promote euphoria. And we have the luteinizing hormone, We have the adrenocorticotropic hormone, ACTH, and we have thyroid stimulating hormone, and all these. But for now, is it only osmoreceptors that can sense a decrease in blood pressure and baroreceptors? Is osmotic pressure the same as blood pressure? If your blood osmolarity is higher or lower than normal, your body reacts to replace this water loss by releasing ADH. If your blood osmolarity is lower than normal, this water loss, osmolarity, ADH leads to increased water reabsorption by your kidneys. Osmolarity goes down and blood pressure goes up. So osmoreceptors in hypothalamus. Hypothalamus gives order to ADH in the pituitary gland, posterior pituitary. It increases the permeability in the collecting duct. Therefore, H2O reabsorption helps prevent further osmolarity increase. Because you are losing water, your osmolarity. So osmolarity is referring to the not the water. It's against whatever substances that are against the water, that are dissolved in water, right? So you want to reabsorb water. Does osmolarity mean higher concentration of solids in water? In other words, blood as the solvent. So based on what we have here, this is the definition of osmolarity, right? And you can see here that when the H2O is reabsorbed, then you have blood osmolarity. You also have a reflex on your thirst, so you drink more water to reduce blood osmolarity to set point. The release of ADH is triggered when osmoreceptor cells in the hypothalamus detect an increase in the osmolarity of the blood. And this is when you exactly get thirsty and you want more water. Blood pressure is sensed and maintained by baroreceptors and chemoreceptors. That is correct. Give the cardiac output equation with their units. So I remember that we have stroke volume, heart rate, and blood pressure. So blood pressure equals heart rate times stroke volume. Heart rate is beats per minute, and stroke volume is liters, and blood pressure is millimeters of mercury. Let's see. We have cardiac output, which is milliliters per minute. And then we have heart rate, which is beats per minute. And then we have stroke volume, which is milliliters per beat. So cardiac output, which is milliliters per minute, is controlled by the heart rate. Both nerves and hormones control the heart rate, beats per minute. And the stroke volume is controlled by blood volume and vascular resistance. So factors affecting heart rate: autonomic innervation, hormones, fitness levels, age. Factors affecting stroke volume: heart size, fitness levels, gender, contractility, duration of contraction, preload EDV, afterload resistance. So stroke volume equals EDV, the preload minus ESV. So age does actually affect the heart rate, but not the stroke volume. Gender, on the other hand, affects stroke volume, not heart rate. Heart size, fitness levels, so it's only hormones and autonomic innervation that affect heart rate. Fitness levels affects both heart rate and stroke volume. And what is EDV and ESV that lead to stroke volume? Blood is considered a what because it consists of blood cells surrounded by non-living fluid matrix called blood plasma. Blood is considered a connective tissue because it consists of blood cells surrounded by a non-living fluid matrix called blood plasma. So it's a connective tissue. Plasma is about 55% of blood. Platelets are 0.01. Red blood cells are 41%. White blood cells are about 4%. We have lymphocytes, basophils, eosinophils, monocytes, and neutrophils. It's a beautiful diagram. Blood is considered a connective tissue because it consists of blood cells surrounded by a non-living fluid matrix called blood plasma. The fibers of blood are soluble protein molecules that become visible only during blood clotting. They transport vehicle for the cardiovascular system. So the blood cells in capillary, as you can see them here, there are the white blood cells and the red blood cells. So yeah. So yep. Red blood cells are also known as erythrocytes, cytoplasm containing hemoglobin. Biconcave discs with no nucleus, they carry oxygen. The main function of what is to lower blood pressure by promoting excretion of water and sodium. It is aldosterone, ANP, atrial natriuretic peptide. Let's see, aldosterone. Where's the adrenal cortex? Mineral corticoids increase water reabsorption in the kidneys by increasing sodium reabsorption, promote potassium and hydrogen ion excretion. Amazing. So the excretion of water and sodium. So ANP is different than aldosterone. As you can see here, it's the opposite. Aldosterone increases water reabsorption, so it increases blood pressure. But ANP, it's, oh shoot, the source of ANP is the heart. It's atria. It's atrial natriuretic peptide. It promotes salt and water excretion. It lowers the blood pressure by excreting water and sodium. Interesting. So there's only one hormone that comes out of the heart, and specifically from the atria, and that is the atrial natriuretic peptide, ANP, to lower blood pressure via reabsorption of excretion of water and sodium. What is the percentage of blood composed of RBCs? I believe it was around 41%. Oh, hematocrit is the percentage of blood composed of RBCs. Normal hematocrit is about 45%. So this is normal. Polycythemia means more red blood cells, and anemia is less blood cells. If you remember, we studied a bit about thalassemia and the fact that the hemoglobin subunits are defected. For example, instead of having 2 alpha, 2 beta subunits, one of the thalassemias had 2 alpha and 2 gamma subunits. I believe that was also the fetal hemoglobin. So yeah, these have different subunits of hemoglobin, but anemia is and that can also result in anemia, right? That's why thalassaemic people are anemic individuals. What is Buffy code 1%? Well, we don't know. There might be a video on hematocrits. What am I writing? We have done white blood cells that are also known as neutrophils, I believe. I'm sorry, leukocytes. Leuk means white, so they are also called leukocytes. They are spherical shape with large nucleus, and they are 8,000 per cubic millimeter of blood. So there's also a video on WBC. RBCs and white BCs are both formed, and they are both formed in bone marrow. Yes, so it's bone marrow that gives the stem cells for red blood cells, platelets, and white blood cells. So, what is the process by which stem cells from bone marrow develop into mature blood cells? I think it is erythropoietic maturation, something like that. Hematopoiesis. Hematopoiesis is so hematopoietic cells are in bone marrow. They give lymphoid progenitor cells for lymphocytes, and then they give myeloid progenitor cells for RBCs and white BCs. So we have myeloid and lymphoid. Myeloid is for and we have this is a beautiful diagram, very comprehensive. You have innate and adaptive. So we have bone marrow, blood, tissue. So multi-potential hematopoietic stem cell, hemocytoblast. Big note, innate immunity is our first defense against invaders. The epithelial, you see how the cardiovascular system is integrated with all these other systems, immune and blood. Innate immunity is our first line of defense. The epithelial and mucosal linings of our respiratory and GI tracts, as well as our skin, are major components of the innate immune system. These act as physical and chemical barriers against pathogens. Cells known as macrophages also play a large role in innate immunity. Macrophages recognize bacterial or viral components such as lipopolysaccharide, LPS, or double-stranded RNA via special receptors known as toll-like receptors. TLR activation causes macrophages to secrete cytokines, small molecules involved in cell signaling and attraction, as well as to phagocytose the infected cells. The innate immune system is required to activate our adaptive immune system. The adaptive immune response is mediated by immune cells known as lymphocytes. These are B and T cells. B cells secrete antibodies, highly specific protein molecules that bind to a specific pathogen. These antibodies bind specific parts of pathogens known as antigens. This is one of the biggest Anki cards I've ever seen. We have mast cells, natural killer cell, macrophages, dendritic cells, monocytes, neutrophils, basophils, eosinophils. So this note is mainly about the difference between the innate immunity and the adaptive immunity. In adaptive, it's specific, so it's mediated by lymphocytes. Those are B and T cells. B cells secrete antibodies, if you remember. They are highly specific protein molecules that bind to specific pathogens. These antibodies bind specific parts of pathogens known as antigens, either presented extracellularly or uninfected cells, or free floating in the body. Antibody binding attracts mechanisms that will then attack and destroy the infected cell or pathogen. Some of these B cells become memory cells, which help the body remember the disease and prevent reinfection. T cells can either be helper T cells or cytotoxic T cells and bind pathogens via the T cell receptor. Okay, I don't know what I'm reading here. How much time is there left? 18 minutes. We'll come back to this. Just to know that hematopoiesis is responsible for creating red blood cells. Sorry for my lack of energy. I've had COVID and I'm in the recovery phase. What are one cell thick and make up the endothelial wall? It's capillaries. So we should know what is the endothelial wall. It's endothelial cells here. Yeah. Aldosterone raises blood pressure by sodium retention and potassium secretion at the DCT. So yeah, it reabsorbs sodium and excretes potassium. The three types of granulocytes are eosinophils, neutrophils, and basophils. Phil equals granulocytes, part of the innate immune system. Innate is not specific, it's not adaptive, right? So these are granulocytes. You can see they have granules, but monocytes and lymphocytes don't have granules. That's why they're called agranulocytes. So they they contain the 5 different classes of white blood cells. So lymphocytes make up the immune system. Monocytes remove foreign beings and dying cells from body. Eosinophils fight parasitic infections. Basophils associate with immune responses. And neutrophils fight bacterial and fungal infections. And here you can see that slide again. The granules in a granulocyte cause inflammation that kills bacteria and fungi. So now we know the function of these granules is to cause inflammation and kill fungi and bacteria, right? The 2 types of agranulocytes are leukocytes and lymphocytes and monocytes. It's lymphocytes and monocytes, so they don't have any granules. This is the monocyte. They are macrophages or dendritic cells. And there's also lymphocytes here. As we can see, the origin of the lymphocytes and monocytes are different because lymphocytes come from lymphoid progenitor cells, but monocytes come from the myeloid progenitor cells. So what is also called something else that are a component of blood whose function is to react to bleeding from blood vessel injury by clumping, thereby initiating a blood clot. So platelets are called thrombocytes, and they are a component of blood whose function is to react to bleeding from blood vessel injury by clumping, thereby initiating a blood clot. So this is the mechanism through which platelets clump the red blood cells. As you can see here, there is a clot which is from fibrin, and these are activated platelets. So I heard that you two finally tied the clot. Sure did. Coagulations. Instead of congratulations, you have coagulations. Funny touch. Can I clot to prevent injury? To prevent injury? Yes. Actually clots and travels to brain like a boss. Stroke time. Actually clots travels to brain like a boss. Stroke time. What pressure moves fluid out of a capillary and into the interstitial fluid? Should be osmotic pressure? No. Hydrostatic pressure? So we have hydrostatic pressure, which is the opposite of osmotic pressure. Osmotic pressure brings fluid back to the capillaries. So hydrostatic versus osmotic pressure. What is found inside RBCs and it carries oxygen? It is hemoglobin. Amazing. Human hemoglobin. Heme. Red blood cell. Perfect. The binding of oxygen to hemoglobin can be characterized as cooperativity, sigmoidal, cooperative. When one oxygen molecule binds to one of the 4 heme groups in a hemoglobin, it becomes more likely that the remaining sites will bind to oxygen. So hemoglobin and myoglobin. So myoglobin has hyperbolic dissociation curve. There's no cooperativity, but hemoglobin has sigmoidal cooperativity and is cooperative. We have the dissociation curves. Myoglobin has higher oxygen affinity. It responds to muscles' oxygen needs. Hemoglobin is cooperative binding. Sigmoidal curve responds to oxygen availability. So the peripheral tissues is in this zone, 50% saturation. The lungs is here. When the muscle is at rest, it's there. When the muscle is exercising, the saturation, the affinity of oxygen goes back in order to dissociate more oxygen to tissues. The key features of hemoglobin, myoglobin is that they are globular. There are hemoproteins, specialized proteins that have a prosthetic heme group. The prosthetic group is a non-protein molecule essential to biological function. Myoglobin is in skeletal and cardiac muscle. It's a reservoir for oxygen. Hemoglobin is in red blood cells. Supplies body's tissues with oxygen. And the Fe2 plus coordinates 6 bonds. It's the center of porphyrin ring. This is called the porphyrin ring. And Fe2 plus is at the center. And it also has, you can see it's connected to 4 nitrogens in the porphyrin ring and 1 oxygen at the top and 1 base, I believe, nitrogenous base at the bottom. It has a taut state, which is not relaxed. So when it's not relaxed, you need more oxygen in your tissues. Therefore, the affinity for oxygen is lower. So lower oxygen affinity. When it's in relaxed state, your tissues don't need oxygen. So the oxygen affinity of hemoglobin is higher for that. You can see that the oxygen disrupts the subunit interaction between the alpha subunits, and myoglobin has a distal histidine heme group and a planar porphyrin ring and proximal histidine. and polypeptide alpha helix segments, planar porphyrin ring. So the porphyrin ring is attached here like this. Fetal hemoglobin has greater oxygen affinity, facilitates oxygen transfer from mother to fetus. The greatest oxygen affinity is by the fetal hemoglobin. It facilitates oxygen transfer from mother to fetus. Is this the right order of O2 affinity by... Is this the right order of O2 affinity by... from higher to lower? I don't know if fetal hemoglobin has higher affinity than myoglobin, but for sure we know that fetal hemoglobin has higher affinity than the adult hemoglobin. If your blood osmolarity is higher than normal, your body reacts to replace this water loss by releasing ADH. So osmolarity, as we know, is the amount of solids. So if it's higher than normal, you've been losing water, so you release ADH. Give the cardiac output equation with their units. So it's cardiac output, which is milliliters per minute, and equals heart rate times stroke volume. Heart rate is beats per minute. Stroke volume is milliliters per beat. Blood is considered a what? Because it consists of blood cells. It is considered a connective tissue. Red blood cells are also known as erythrocytes. Oxygen binds to the Fe atom inside a heme group, iron atom inside a heme group. The structure of coordination complexes is always the center being something super electropositive, aka a metal, whereas the atoms connecting to the center atom are electronegative, aka non-metal. So the center is electropositive, a metal. The atoms connecting to the center are electronegative. Structure of coordination complexes. What are coordination complexes and where are they used? CO2 and H plus will trigger the heme group to CO2 and H plus will trigger the heme group to release its oxygen. How? CO2 and H plus allosterically inhibit hemoglobin. This means oxygen is released near lots of CO2, or in acidic sites, which is where respiration is happening and oxygen is needed. So the factors affecting dissociation are blood temperature. If increased blood temperature, it reduces hemoglobin affinity for oxygen. We knew that from the dissociation curve shifting to the right. So temperature. So we had CAT A mnemonic, right? You have CO2 acidic, 2,3 BPG, temperature, and exercise. So we know that with those factors increasing, you shift to the right, and shifting to the right means that the affinity for oxygen is high, is lower. And we need to know that they allosterically inhibit hemoglobin. Our timer is on, so we can stop here and come back later. For now, peace.